Так, agreed, but let's say January. Do what you want, but let's show must go on. Starless Google. Who is Starless Google and why to speak? to do something. Yeah. We need to do something. I need to show myself. So, what I got for today? My lecture is Fourier transform of non-periodic signal. We saw Fourier transform before, yeah? It's usable thing, but in its classic form, it's only for periodic signal. Signal should repeat itself. What I want to draw? Okay. I need to draw something. I'll draw nice building and very unhappy investor jumping from this building. It's it's huge, it's a bank. Guy know about the crisis and jump from the roof. What's the signal we will record? Something like this. It will be paused. I can say, okay, take this as a one period and perform a Fourier transform. You need to analyze, for example, I'm asked to analyze impact on underground communication. This is underground tunnel. What happened with the underground tunnel when unhappy investor jumped from the roof? I can try to decompose this into Fourier row, but there will be a problem. If I take this as a period, I will receive a Fourier row. Yeah, fine. But this row will correspond to what? To the periodic signal. Like here is a row of unhappy investors going one by one, jumping one by one. With the period of T capital. Unhappy. Okay, this one is unhappy. They all are unhappy. They listen what Trump is coming to power. This is not realistic. I would like to have my mass model in somewhere reflecting the reality. Only one jumped from the roof and only one impact was on the underground sewer. Not a row of them. That means I need a two. It's not, how to say, normal to open cans with the shovel. We dig with shovel and open cans with can opener. So I need a tool for a non-periodic signal. Where my TV work? I stand here. I would like to use as my, let's say, training rabbit, very classic process. It's one of the electrotechnics basics. It's a capacitor discharge. At a zero time, capacitor charged to the E volts discharges through resistance, producing a pulse U from T. Time do I have? Here it is 0 when time is less than 0, and this line is e power minus alpha time, where alpha 1 against x. Classics of the classics. Here, I have created a sequence. This one, something familiar? Have you heard about transients? Something. Oh yeah, what I'm talking about. Have you any? Where am I? Yeah. I have my test bench. I can bring camera close. Okay, I have my capacitor. It's adjustable, just 100 years old, and my resistance. But all is powered from this pulse generator. I use special pulse generator. It produces 1.5 microsecond pulse, I do like this, each millisecond. Approximately. Yeah, here's my generator producing 1.5 microsecond pulse each millisecond. Yeah. Yeah, 1 second, I'll draw schematic. Yeah, 1 second, I need a schematics. What this pulse generator is doing. Idea. I have something like this. Connected to the diode, to the capacitor, my resist, and this will be output signal. How it works? This one is 1.5 microsecond, and timing is somewhere around 1 millisecond. Short pulse, approximately 1000 times shorter than the period. Capacitor charges the diode and then slowly discharges. My capacitor is 1 nanofarad and the resistance now of 100 kilo ohms. I see a nice repeating sequence of pulses. What's good in the sequence? Oh, here is the sequence. What's good in the sequence? It's repeating. It's easy for me to work with it. We have a nice sequence of my pulse. If one pulse, let's say, this one is not 10 equals to E minus alpha 1. So what will be the mass for this sequence? This sequence following one by one. All the sequence can be written as sum of minus infinity to infinity uno. Here m is an integer, so it's a sequence of sum or repeated pulse. I'm repeating one pulse, one by one, one by one, one by one. Now question, can I apply a Fourier transform to this sequence? Does it look like a periodic signal? Yeah, it's repeating. We have nice period. My generator creates it. My generator. Like ohm. I can apply Fourier transform. Nothing stops me. So, complex amplitude for the harmonic will be divided by period. I should integrate in the margins of half period a power minus in time. Yeah. And now I can do one trick. What will happen if I increase repeating period till infinity? Leave my sequence. Take a look at my scope. Frequency 2.2 kilohertz. What will happen if I extend period? And I can enlarge my period. Wait 1 second. Signal has a frequency of 1.3 kilohertz. Yeah? And next moment No period found. Why no period found? What happened? Periodic, 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 periodic. Why? What happens? When the time ends for my school? Here time begins, here ends observation window. Here is the end of time for my school. Nothing after this line. So if the next one when next pulse is seen, signal is periodic. No signal. Signal is not periodic, not repeating. For my scope, times end here. If I increase time infinity, who cares about pulse after the doomsday? When this word ends, who will care about the pulse? Yeah? Pulse. All repetitions next and previous will become void. Nothing happens here. If the next pulse is where? Here is the end of time. If the next one occurs after time ends, nothing occurs. No one will see it. If so, I can write what? Okay. What can I write? At omega k, where omega k is double P divided by period, 2 divided by time, minus infinity to infinity, f power minus j omega k time, Nice formula. Nice? Nice formula. But here, what I will have? 2 divided by infinity. What's the result? 0. And this formula is useless. Not at all. I still have this part. It's not 0. It's something. I can use it. Theory of signal. Name it as a spectral function. Infinity to infinity. Who's writing infinity like this? My pulse, a power omega. The name for this is spectral function. It's a complex function of the frequency. In previous, I need to point. In previous we saw what? For periodic signal, it's Fourier, let's say it's decomposition to Fourier role, or its Fourier kind of image was set of real frequencies at 1 omega, 2 omegas, 3 omegas, and so on. It's a physical device producing physical signal. This one is a pure abstract. It cannot be touched, cannot be tasted. This thing do not exist in our world. It's a pure abstract object image in a frequent space. Continuous frequency function. Okay, I got something imaginable. How can I use it? What's the idea? Where is my profit? Why do we need this strange object? This one. Three. Let's say I have a circuit. Very simple circuit. Oh, sorry, this should be. I can write O Y S A O X multiplied by F and divided F 1 against J omega C. Very simple. I can write U Y as a transfer function multiplied by Ux. Very simple. Transfer function is a function of frequency. If I supply function of frequency with something being function of frequency, what will be the result? Something dependent on frequency. Looks okay, yeah? So, if we have something can be described as a transfer function and input will be spectral function of something, result will be transfer function multiplied by input spectral function. Looking a bit more profitable, yeah? But how did I get this one? I had something in our space being function of time. With the help of Fourier transform, I got this. You just saw this nice form of Fourier transform. I can, let's say, transfer this to frequency space or create an image in frequency space. Fine. I can put here in frequency space, many things are much simpler. In time space, I should solve something with 1 to time. This is capacitor voltage in time. Not a nice function. But at this point, my result, it's near, but I can grab it. Why? Because it's in frequency space. Our space is a time space. Maybe I can very easily perform calculus in frequency space, but this all will be absolutely useless, works nothing until I can get a result in my time space. So what I need? I need a way to perform an inverse Fourier transform. This will give me a result in a time space. In my something what I can grab and use and bring to my boss. I need not only way to the wonderland, I need to way back, and to get back I need inverse transform. What I can say at first? At first, one moment. I will repeat. Let's say I have period less than infinity and greater than 0. In this case, okay, something will be nothing when the value of the spectral function at a frequency. This is important moment. The classics, this classical Fourier rule, these coefficients can be obtained as a values of spectral function at a particular frequency. Select some repeating frequency and values of spectral function will give you what? Fourier rule. It's one of the way how to perform this transform numerically. Just select. What can you do? You can cut at the border of the frame. Let's say in theory, this exponential decay is infinite, but in reality, here, take a look. 100 milliseconds, 200, 300. If I cut at 400 milliseconds, this tail changes nothing. So I can compose a classic Fourier rule, but cut my simulation at, let's say, this point at 400 milliseconds, ignoring this tail. It what can be done numerically. But now let's try exact formula. Let's try to get exact formula. So what should I do? I will write what I know about this. So how I get this signal? I started from the sequence of pulse. Infinity to infinity. I started from the sequence of pulse. This sequence can be represented as a classic Fourier rule. Infinity to infinity. A power double P time on. Here it's a substitution with the Fourier rule. We saw it. And harmonic factors or harmonic weights, I can get them as values of spectral function. So it will be 2 divided by period, 1/2 goes forward, something from minus infinity to infinity, spectral function of frequency. No, let it be more precise. As power dot and time. Yeah, here it signal is the sum of all pulses in sequence. Sum of all pulses in sequence can be represented as a Fourier row. Fourier row factors are taken as a values of spectral function, and I note what this spectral function is a Fourier transform result of my original pulse. A lot of lot. Can I go forward? Looking for 3, 2, 1. Nice, nice, nice. A lot of formulas. Sometimes professors are paid for formulas. No. So let's analyze. What will the limit if I increase my period infinity of my sequence? To infinity. What will be the result? Whoop. Same trick. One and only pulse. Because all other are where? Outside of the observation frame. Nobody and no one sees them. Okay, this is easy. Now the next one. What will be a result? Come on. Sum of from minus infinity to infinity of my spectral function taken at points double p divided by a power k double p divided by time. This one bit tricky. Here I would like to draw your attention to one moment. Here, let's say, is a spectrum of some signal. Value of AK. Frequency 0, 1, 2, I don't know, 3, 4, so on. Spectral lines. What's this 1? 1 omega or 1 double P divided. What's this 2? 2 double P divided by time. You understand this? How the spectrum chart is forming? Where am I? Yeah. What's the distance between the lines? between next omega and previous omega. What is this distance? What's the step of spectral lines? One frequency, double P divided by period. Yeah? What will happen with this chart if I increase period infinity? Lines will be closer and closer and closer. And what will happen? At one moment, I will have one, let's say, area or figure. So, sum will become an integral in frequency. You understand what? You draw lines closer and closer and closer. At the one moment, the whole line become one united figure. So this sum becomes an integral. Actually, calculus of this sum becomes what? Area of the figure. Task of calculating the sum will become at the limit will become a task of calculating figure area. So I can write, what can I write? What I need a limit of 1 double P sum from minus infinity to infinity my spectral function f power your omega and multiplied by omega next minus omega previous. Yielding at the result one again double P in minus infinity to infinity from omega. It's a complex f power of omega d omega. So my will be here it is. Here is required inverse Fourier transform in a mass form.
I'm not understanding very well. What are we aiming to do with
what we are aiming to do, see where idea is. At first step, I have some, I don't know, circuit, some object, what can be described with kind of property in the frequency space. And we need reaction of this. We need to know what happened if we apply, let's say, something like this is input something. Absolutely not mandatory, but it's an electric. It can be shock. For aeronautics industry, it may be some kind of disturbance, so on. This one is can be achieved by analyzed object in a frequency as a frequency characteristics. I would like to know results, output. What can I do? Analyzing time function is very labor consuming because these equations are not very easy to solve. What can I do? I can apply here Fourier transform on x. This will yield me spectral function. Something abstract, but it's a function of frequency. In space of frequency, mass is much easier, analysis is easier. The only problem, results, what I will get? Frequency function. What's here? What's between? How can I, from frequency, come back to time, to reality? This one is answer. Here, I will draw it in red. This is output from the frequency space. It's kind of magic pill. And you in real time.
Okay, but the goal of the spectral function is only to simplify
the goal of spectral function is to create an image of something in time, but in this magic frequency space.
Okay, so it's to simplify the
yeah, it's to simplify analysis of the system. Because analyze in function of frequency is much easier than in time. Well, if you don't believe me, graphic equalizer is a simple thing. Graphic equalizer is function of what? Have you? I should ask. Did you solve graphic equalizer in your life? Really? Today, not any device comes with this nice function. Hertz to shift, I don't know, 250 to select, 1 kilohertz to select, 2.5. Something like this. Yeah, you never saw it. Yeah. What is the function of? If you analyze it from the mass. This one is an amplitude. Or decay or amplification. It can be 0 dB at a middle, below decay, up amplification. And what will be on horizontal? Frequency, of course. It's a function of discrete frequency. Yeah? In reality, box, the equalizer box, we have input signal, we have output signal, but what we create with the equalizer box? It's a transfer function, but from, let's say, I omega at a discrete frequencies. Yeah, it's a transfer function of discrete frequency. Because you can draw only 100 to 100 and you cannot change any frequency. So it's a function of discrete frequencies. Can you imagine the same but as a function of time? It's easier to kill you. Yes. What there is one moment, because at the basis of this exponential form of Fourier transform is Euler's formula. I can always write what spectral function of minus frequency is a conjugation of spectral function of positive frequency. This means what I can use only real part of the frequency space. It's very simple. If you have x, a plus would be, and it's conjugated, a minus would be, will be double a, double real part. Sequence. One moment, we will analyze sequence. Let's do something with my sequence. So I have one pulse being 0 when time is less than 0, and E is alpha, it decaying exponent if time is greater or equal by 0. Here in my case alpha 1 divided by RC. Let's try to get its image in a frequency space. Corresponding spectral function, how can I get it? Minus infinity to infinity, a power minus j omega t. In my case, what I will get? A from the integrate I need to 0 to infinity, and of a omega t dt. A divided alpha omega. K is my spectral function. So in frequency space, this one represents as E divided by alpha. I'm changing alpha. And divided by omega. I'll do small trick. It's impossible to draw this function. But I can separate it into a real and imaginary part. I can write it as E divided by square root of alpha square frequency square F power arc tangents omega divided by alpha. frequency. This line is my spectral function divided by its maximum value. Here will be 1. I'll draw it in, let's say, in percentage. This point is 100%, and 50% point corresponds to the point double alpha and minus double alpha and alpha. This is approximate view of its magnitude. And can I take a sequence? Let's say I have period less than infinity. This will mean what I will deal with the Fourier role being double 2 divided by period multiplied by e divided by square root of alpha square plus double p divided by period again square multiplied by f power minus j arctangents of v double p divided by period divided by alpha. Here. Nice formula, isn't it? Sequence. Okay. Sequence. You know, my scope, sometimes I'm afraid of my scope because it's smarter than me. My scope is smart enough to perform a discrete time Fourier transform on the signal. Yeah, now my scope is performing a discrete time Fourier transform on my signal. Yellow is a sequence of with this period. At this moment, half a millisecond. Frequency is 2 kilohertz, so no, 1/2 of a millisecond. The red line, can you see the red line? Is a set. It shows absolute values of frequency components. Here, the red line is a representation of my signal in frequency space. The spectral function, if you connect all these points, will form kind of borderline or limit line. If you connect like this, it will be a spectral function. Now, what will happen if I change a period twice? How do you think? What will happen? I will take, let's say, 3 as double period. What will happen? Any ideas? How will change my signal in frequency?
do it in
Can you see? What happens? The greater distance between pulses. What happens with spectral lines? You see this? More points for the cut points. You'll see it clearly. Help me sleepy. No, it's cold. You see, the closer pulses. What happens with the distance between spectral lines? Greater. Because period here is undivided. The higher distance between the higher period, closer are spectral lines. You see they coming closer. The closer distance between pulses, the shorter period, the higher is distance between spectral lines. See? Now, what will be a reaction to alpha? I'm changing capacity. See what happens with spectrum. What happens with the spectrum? What can happen with the spectrum? One second, only one wire. I will do one trick. I will add this 100,000 ohm resistor to my circuit. I will try to make it more visible. You come here. Not 100 but 200. Yeah. Now I have 200 kilo ohms and I'm ready. I have the switch. Simple switch. Simple switch. Yeah. Now resistance is only 50,000 kilo. 4 times I decrease resistance 4 times. You see what happens with the yellow line? It's a change of alpha 4 times. Changes are much faster. See? And what happens with the spectrum? Slow changes, short spectrum. Slow changes, I need relative small frequency band for my signal. Sharp changes. You see what happens? Frequency area needed for my signal changes 4 times. You see? Where's the end, where's the tail of the signal? Nothing here, signal here. Nothing here, signal here. So the faster changes, the wider will be a frequency band or frequency area of the signal. Slower distance in time, higher distance in frequency. Longer distance in time. Spectral lines are closer. Slow changes, short spectrum. Fast changes, wider spectrum. So fast changing signal takes wider frequency band. Slow changing signal takes less frequency. And also, in sequence, the higher distance between pulse, the closer will be spectral lines. And what's at the end? Can we analyze what at the end? I need fastest possible signal. To understand what at the end, I need something fast. Something ultra fast. I want to know what at the end. What at the end? To understand what at the end, where all this leads us. I need another one abstract object. At first, let's say we have something like this. Time, we have a pulse in time. I can call it delta minus t by half, tau by half. And its amplitude, k is 0, is 1 against tau. So is 0 when time is less than minus by half. 1 against tau time and 0 times time is rho of t by half. Area of this rectangle, go from minus infinity to infinity, equals to t by half, t tau by half. 1 against tau z is 1. The area of this, call it, okay, it's a rectangle. I name you rectangle. So this area of this is 1. Why should someone draw out with the area of 1? It's at some amount of time, some point in time. We just saw 1 second. I will clarify. Now it's symmetric time. It's something in time. Just a piece of time. 1 second. I'll be back in a second. Can we take into consideration let's say we have time, some, I don't know, something. This is, and I would like to multiply it P0. This is my delta function, but shifted in time. I would like to analyze what will be the result if I calculate area of this multiplier. Zero. Yeah, this will correct. I would like to analyze this. What will be value before this time is 0 minus tau by half? 0, because multiplied by 0. And after this point, 0. So I need to only T0 minus tau by half, T0 plus tau by half. Minus 0. For any real white line, for any real signal, I can select tau small enough so these 2 points will be near equal. I can select this time small enough to achieve what? What? Oh, T0 minus t by half will be approximately plus tau by half. This allows me to approximately write my OS T0, its average value. Here I will have T0 minus tau by half, T0 plus tau by half, tau. And what's the value of this integral? 1. We started from this. So it will be something familiar, not? What can it be? Remember my student taking a values of experiment, or analog to digital converter taking a samples. It's a sample. It's one measurement. It's one measurement of analog to digital converter. Understand? If you multiply something with this function, you take a sample of it. Yeah, there is one moment. This should be small enough. What about digital electronics, sample and hold device? Special device to...
Okay, sorry. So is it okay to treat that function like an impulse function? According to the integration property, it's more like a function, it's an impulse function.
Yeah, it's one very short part. Actually, at this moment it's quite shake because I'm speaking. Let's take tau small enough for sample and hold device. What's doing sample and hold device? Who studied digital electronics? Simplest sample and hold device, ADC itself, and here is something we need to convert to digital form, and we have a sampling pulse. Do sample, do sample, do sample. At a sampling pulse, it shows capacitor charges, then disconnects. Here we need an amplifier with very high input impedance, so it will hold value until analog to digital converter finished its work. This is the way we will always have this, let's say, uncertainty time limit with the switch property. since I can use any time, what can I write? What? Minus infinity, sorry, it's infinity to infinity. 1 times delta t minus t0 t times approximately equals to voltage time t0. And also I can substitute whole signal with the sequence of what? Minus infinity to infinity. I need to introduce some variable, but this will be delta x dx. What this equation tells me? If I substitute integration with some, let's say, extra variable, this allows me to represent my equals time as a set of these are deltas. You understand what I'm doing? I can substitute my signal with samples. Here is a question because I have some tau greater than 0. But this thing tells me that my signal can be substituted as with a set of samples. Yeah. Your digital sound is a set of samples. I started to speak on ultimate limit of fastness. Fastest thing possible. Fastest thing possible will appear if I will analyze what's the limit when tau goes to 0. It has a name, delta function. Delta function equals to 0 when time is not 0 and infinity when time equals to 0. Not 0. It's kind of absolute thin needle going to infinity. It's absolutely fast. But area of E is still 1. And minus infinity to infinity delta t minus t0 equals to 1 t0. What's this? Absolute sample. Absolutely fast analog to digital converter. Ideal sample. Infinity fast. If God will have its own ADC, it will be absolutely fast. It's a good analog to digital converter. It's absolutely precise, has no error. It's equal, absolute. Also, they can be written as minus infinity to infinity delta not t minus x dx. One moment, you'll see what's that. What comes of this? I can also write one thing. What? What a thing. I can write minus infinity time t0 equals to 0 t0 1 half t equals to t0 and 1 is greater than t0. And what? What behind it? One. Switch on function. Switch on function. One of equals to 0 that less than 0 and 1 and that is greater than 0. Switch on function. Delta function is nothing than a derivative of the absolute ideal switch on function. Switch on function. Yeah. Now, what about frequency space? In time space, delta function is absolutely fast pulse. Fastest of them all. Father of fastness. Nothing can happen faster than the delta function. Spectral function of the delta function will be minus infinity to infinity, let's say t0 at power minus omega equals to a power dot omega 0. In case t0 is 0, spectral function of simple depth. So if we could form Fourier transform of spectral function, what we will get? If you put here 0, you will get 1. Do you understand what I'm writing? I'm just writing. Infinitely fast function takes all frequencies, will occupy all frequencies with the same amplitude of 1. We told what if faster changes mean wider spectrum. Something absolutely fast takes all frequencies. We'll have a uniform spectrum on all frequencies. It's a bad news when you try to do an electric or magnetic compatibility task of something fast. Because spectrum of noise will be very wide. And making your life, you will not be happy. Okay, I can do one more thing. I can do one more trick. I can do one more trick. Okay, I will write one more form, one more idea, and we will take a break. Don't die. So, let's say I have ideal harmonic signal. Cosine of omega t, let's say omega 0, plus some kind of v0. Spectral function for E, what it will be? Max should integrate in infinity. Lagrange's cosine omega 0 time plus phi0 a power of omega time theta. Yeah? Minus. Yeah. What I need to do, I need to substitute cosine with exponential function using Euler's formula. I will use Euler's formula to substitute cosine with exponent. This means what I will write something like this. Equals to max by half minus infinity to infinity a power omega 0 time plus phi 0 plus a power minus j omega 0 and minus phi 0 minus 1 no plus only here and multiplied by a power minus j omega d k is multiply sign. I need to multiply. We can do one trick. We can, to solve this, let's say to present it in more human-friendly form, we can introduce a delta function from frequency. It will be 1 divided by double p minus infinity to infinity a power j omega x dx. This allows me to say what 1 again double p minus infinity to infinity a power j omega plus or minus omega no not 0 not important x. The x will become a delta function from omega plus or minus omega 0. It will become an offset delta function of frequency. Now, spectral function of my ideal voltage will be V O max multiplied by F power V0 multiplied by delta function of omega minus omega 0 plus F power minus V0 delta function from omega plus omega 0. Really, my ideal signal can be represented with a two infinitely thin spectral lines at a frequency omega 0 and minus omega 0. My signal, ideal, I have only one frequency. It's an ideal harmonic signal. Its representation in frequency space will be two infinitely thin spectral lines. And final, one more formula. If I perform a Fourier transform on pulse sequence minus infinity to infinity plus m, performing a Fourier transform on impulse on pulse sequence, I will get double P divided by period multiplied by sum from minus infinity to infinity double P. Okay. That is a Fourier transform result. It's a spectral function of my original pulse multiplied by delta function of omega plus k double T sequence of pulse will be represented, will result spectral function of one pulse but placed a kind of discrete, it will have discrete components at a frequency, let's say, it's kind of frequency cone. It's a function of discrete frequency on a frequency k double p divided by I. It will have discrete spectrum in frequency. And if someone tells me what this spectrum isn't discrete, is it continuous? No, it's discrete. So sequence of pulse will have spectrum of one pulse placed or represent as a discrete frequency function. Okay, enough for this moment. You can take a break. How many lectures we have today? 2? Ha 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 ha. Maybe some questions? Where can I kill you myself? Don't worry, don't worry.